All right, one more video for 8.1 where we talk about the law of sines. This video will be pretty similar to the previous video where we're examining this ambiguous case, but I wanted to make another one because, well, two things. The ambiguous case, it's just hard. It might help to see it again. And then also, when you get around to doing the homework, what you'll see are a lot of the angles are what you might call unfriendly, meaning that they don't correspond with points that you have memorized off your unit circle. So I just want to show you what you can do in that case, just so you don't waste any of your time just trying to figure out how to get the system to like your answer. So here's our example. We have a triangle ABC, and again, we assume that the little letters are across from the capital letters. So side A is across from angle A. And note that we're given two side lengths and one angle, and that angle is not the included angle of these two sides. Maybe having a picture will help to reference. So I got angle A here, which measures 20 degrees, and then side B, maybe I'll put it up here, and this is 7. And then I know side A, so the side opposite this angle, the one that's over here, has a length of 5. And I think what's going to end up happening is it can either connect my triangle over here or connect my triangle over here, because this side length C is unknown. So it can be this shorter red version or this longer blue version. So I think what we see in this example is there'll be two different solutions for the triangles, and what I want to do is solve both of them. So in either case, what I want to do is solve for angle B, which will either be this angle in blue over here or this angle in red over here, because again, we're going to find that there's two possibilities for that angle measure. And either way, the way I want to solve that is kind of using this information to set up my law of sines. So the sine of A over A is equal to the sine of B over B. I want to solve for capital B, so I'm going to get this all by itself by multiplying the little b up to this side of the equation, and I'll get that the sine of capital B is equal to little b times the sine of capital A divided by little a. Plugging in the known values, b is equal to 7. I have the sine of 20 up in the top here. And so here's where things get kind of tricky. The sine of b is equal to whatever number this is, but I think what you'll see is this is not a value I've memorized off your unit circle. In fact, I don't even think you know what the sine of 20 degrees is. I don't even think that's something you can come up with off your unit circle. So what are we going to do? Well, we got choices. One thing you could do is use arcsin. You could say that b is just equal to the arcsin of this whole mess, 7 times the sine of 20 degrees divided by 5. And this is perfectly acceptable, but there's some things you have to be careful of. The number that we get if we calculated 7 times the sine of 20 degrees divided by 5 would be some y-coordinate. And there's two different angles on my unit circle that have that y-coordinate. One over on this side and one over on this side. The one over on this side is an acute angle between 0 and 90 degrees. And the one over here is an obtuse angle. It's greater than 90 degrees. So in my picture, the red one corresponds with this red one, and the blue one corresponds with this blue one. Arcsin, remember, only gives you values that are on the right-hand side of your unit circle. Because sine is not 1-to-1, we have to restrict its domain to make it 1-to-1 so that we can define the arcsin function. And the way we restrict it is two values from negative pi over 2 up to positive pi over 2. What I'm saying is the answer that you get out of arcsin will never be an angle that's more than 90 degrees. So in the case of this picture, this is telling me the angle in blue. It's not telling me the angle in red. But if I know this angle in blue, I can take advantage of some symmetry. If I notice that this angle here is the kind of the same measure as this angle over here, so to measure the angle in red, I can kind of think about it as going a full 180 degrees and then back by whatever this angle in blue is equal to. So if this expression right here represents my angle in blue, my angle in red would be 180 degrees minus this whole thing, the arcsine of 7 times the sine of 20 degrees divided by 5. You're like, wow, this is getting a little bit crazy. Yeah, we're only getting started. Here are our two possible angles for B. But that's not even the end of the problem, right? Then we'll have capital A and capital B. We'll still need to figure out capital C and then little c. Here's where you have an option. You can leave these exact like this. This could be your answer. You can type this into the system. However, if you type this into the system, you have to be really careful with your units because all of the trig functions and inverse trig functions it thinks are in radians. So you can't type in the sine of 20 degrees. You would have to type in the sine of 20 pi over 180 to convert this into radians. So it would be 7 times that number divided by 5, which is what would have to go into your calculator. And then we're taking the arcsine of that mess, but again, arcsine is assuming radians. So we have to put radians into the sine function, and radians will always come out of the arcsine function. There's a problem. In the homework, you'll see that it wants degrees. This answer is in radians. To convert this to degrees, I'd have to multiply this by 180 over pi. Similarly, if I was trying to enter this angle, the obtuse solution, the angle that's greater than 90 degrees, the one depicted in red here, I would have to write it like this, where I'm converting my angle into radians first so that I can use the sine function. And then when I get an angle out of arcsine, I have to convert that back to degrees since the homework says it wants the answer in degrees. I personally prefer to keep these things all exact like this, to type them in as big expressions, but I think most students don't. I think students don't like typing this stuff in. It's just too complicated and hard with all the different parentheses, keeping track of what unit you're in. It's just annoying. Another option is you could use a calculator. Just be careful if you're using a calculator because the homework system has built-in tolerances that are specified by whoever writes that specific homework problem. So sometimes it needs to be correct to 2 decimal places, sometimes 3, sometimes 4. My advice there is just leave a whole lot of decimal places, and then that way you'll be close enough no matter what. If you're using a calculator, you got to tell your calculator whether all of your units will be in degrees or radians. So for example, on this calculator, I hit mode, and then I can tell it radians or degrees. So if I just change my calculator into degrees here, then it'd be really easy. I can just type in the expression that I have in blue. I could say my answer is the arcsine of 7 times the sine of 20 degrees, because again, it's thinking degrees now, divided by 5. And this will spit out an answer in degrees because again, I'm in degree mode. This 28.6 is what this is equal to. If you were doing the homework, you'd probably want to be more precise than that. So maybe you'd call it 28.6089. Sure. If you don't want your calculator in degrees, or you don't know how to turn it into degrees or something, and you're stuck in radians, that's totally fine. You could still use a calculator. It's just now you have to type your answer in like what you see in green here. So I'm again going to take the arcsine of something. That something is 7 times the sine of something, except now it's not the sine of 20 degrees. It's the sine of 20 pi over 180. Pi is hidden up above this key in my calculator, so I hit second and then this up arrow to get it. I'll close those parentheses, and then I'll divide by 5, and then I'll close those parentheses, the one on arcsine, and then if I hit enter now, it'll give me my answer in radians. I don't want it in radians, I want it in degrees, so I'm going to multiply that by 180, and then divide it by pi to do the last conversion. If I did everything right, I should get the exact same answer here. I do, this 28.6089. It's worth pointing out that 180 degrees minus this 28.6089 roughly is what, 151.3911? And since I've used up 20 degrees for A, my value of B can be either of these two, and I won't exceed my total of 180 degrees. So both of these are legitimate solutions. In this case, there really are 2 different triangles that satisfy this criteria. One of them has an angle B approximately equal to this number, and the other has an angle of B approximately equal to this number. I'm still not done, but I think the worst is behind me. I still need to know what angle C is equal to. However, if I have angle A and angle B, it's pretty easy because angle C will just be 180 degrees minus those 2 guys. The 3 angles together have to be 180 degrees, so it's just all 180 minus whatever I used up on these 2. So 20 degrees and then another this number of degrees. You can use the decimal approximation, or you can use an exact answer, whichever you prefer. Similarly, over here, I could figure out angle C by saying I have 180 degrees total to work with, but I've already used up 20 degrees for angle A and 151.3911, if I did that math right in my head, for angle B. So what's left over is what I have for angle C. I guess these are worth calculating. This is 171 and this stuff, so I believe what I would have left would be the 8.6089. You could check that with the calculator if you feel like it. And then over here, what I would have left would be 20 less than this number. So I think it would be 131.3911, whatever. You could type 180 minus this sum into your calculator, and I'll think you'll get these 2 values right here for your angles of C. If you wanted to type these exact into your homework, what you could do is you could copy this entire expression right here and put that in instead of the 28.6089 number. So you could type in 180 minus parentheses 20 plus, and then this whole mess, and that should give you this exact same answer in an exact format if you prefer to do things that way. I think most people do not. Finally, to find little c, I'm going to use the law of sines one last time. So I'm going to need the sine of capital C divided by little c for sure. And then for my other fraction, I can either use the sine of b over b or the sine of a over a. It doesn't matter because I have answers for all of those numbers now. However, the numbers for b are kind of ugly, right? That's this thing that I calculated. So why don't I use the a's just so stuff works out a little bit nicer? Why don't I say sine of capital A over little a equals this? And since the numbers are kind of ugly, I'm going to solve for little c before I plug anything in. So I'll multiply the c up to the top over here. I'll divide sine of a down to the bottom over over here and multiply little a up to the top here. And I think when all the dust settles, I'll get that little c is equal to a times the sine of c divided by the sine of a. And now I can get my final answer just by plugging in numbers. Remember, a was given to me in the problem to be the number 5. So I have 5 times the sine of c. Probably make the most sense to just use this number right here. But if you felt like being precise, you could type in 180 minus this entire expression right here. For the sake of saving this virtual ink that I'm using, I'm just going to type in the approximate expression and get an answer that's close enough. And then I divide by sine of a. However, I know that a is equal to 20 degrees. So my answer for C would be this. However, you got to be really careful since I'm using the sine function. Both of these angles are measured in degrees. But if I'm going to type this into the homework system, these have to be written in radians. So I'd have to say C is equal to 5 times the sine of this number times pi over 180. So 131.3911 pi over 180. That's just converting that degrees into radians, divided by the sine of not 20, but 20 pi over 180. Again, converting it into radians. It looks like I kept 4 decimal places in here, which is probably sufficient, but I just want to make the point about rounding that if you use a rounded number inside a function like this, it can throw your answer off by more than you rounded by. So if this problem said, please enter your answer correct to 4 decimal places, I wouldn't recommend just keeping 4 decimal places here. I'd recommend keeping, I don't know, like 6 decimal places up here, because if you're going to use a number that's rounded, you want more accuracy than you need for the final answer to make sure that your final answer isn't off by more than it demands. Hopefully that makes some sense. Since I've come this far, I suppose I should solve for little c over here. I can kind of exploit some of the work that I did. Little c, if you use this law of sines formula, is a sine of capital C divided by the sine of a. But a lot of this stuff is staying the same. A is still equal to 5. And then I have the sine of, instead of 131.3911 being my degree measure for C, I have 8.6089 being my degree measure for C. And then I divide that by the sine of 20. And again, just like we saw over here in blue, if I wanted to put this into the homework system, I'd have to convert these degrees into radians by multiplying each of them by pi over 180. One last example that I want to show you. I'm not even going to work through this whole example, but I just want to show you what happens. I'm going to use the exact same numbers that I had up here, where A was 20 degrees and B was 7. But I'm going to change A from 5 down to 2. In terms of my picture, this is still 20 degrees, and this is B here. This is still 7. So I don't know, maybe this is 7 units. But now the side length over here is only 2. It's really short. It's not going to be long enough, no matter which direction I point it, to get down to this side. It's impossible to have a triangle with capital A equal to 20, B equals 7, and A equals 2. What happens if you try this? Well, when you use the law of sines to solve for angle B, you could set things up this way. Sine of A over A equals sine of B over B. And then you could solve for sine of B by multiplying the 7 up here. And you would say that the sine of B is equal to 7 sine of 20 divided by 2. But 7 times the sine of 20 divided by 2, if I refer back to my calculator, remember my calculator is currently in radians. So I would type that in as 7 times the sine of 20 pi over 180. Since my calculator's in radians, I got to convert all of my angles into radians if I want to use sine or arcsine. And then I will divide that by 2. And that gives me this number, 1.197. So what this is saying is the sine of B is equal to 1.197. So what is capital B equal to? You're like, it's just the arcsine, right? Take the arcsine of that number and you're done. Well, what you'll see if I try to take the arcsine of that is I'm going to get an error. You'll be like, an error? That's weird. You must have put in something wrong. No. This is just my calculator's way of telling me that I am asking it for an impossible triangle. In order for this triangle to make sense, I would need an angle B so that the sine of that angle were 1.197. But that's not possible. The sine never gets bigger than 1. The sine is the y-coordinate on your unit circle, and the highest ever gets is this point 1 up here. So there is no angle B, so that the sine of B is 1.197. The arcsine of that 1.197 gives me an error on my calculator. There was one problem on your homework where this happened, although I'm deleting the problem on your homework because I'm starting to think this homework's going to be too hard. So this is just extra information that I wanted to throw in because it was supposed to be something that I'm going to cover, but it didn't show up on the homework and it sure would never show up on a test. But just wanted to let you know that this is what happens if you try to use the law of sines on a triangle that can't possibly exist.